Yes, so my method is about designing Datalog templates for synthesizing bidirectional program from Tabular examples. I'm a PhD student in Stuttgart University in Japan, and this is a collaborative work with Professor Kanae Tsushima from National Institute of Informatics Japan, and Professor Zhenjiang from Peking University, China. In the next slide, slide two, um, one of the key concepts in my talk is bidirectional programs. This is a program expressing bidirectional transformation in the consistency between multiple data in different formats. But but in addition to a relational database, uh, bidirectional transformation, bidirectional programs also apply in many areas of computing, like programming language, software development. Next slide. Generally, a bidirectional program is a pair of forward program get in the red text and backward program post in the blue text. Get in the right side, you can see the figure of the two programs. Get define a new V over the source S and put accept an original source S and updated view V prime and translate to an updated source S prime. To ensure the consistency, these two programs get and put must satisfy various these properties. Get put and put get. The first property means if you have the VV by this is the result of getting over the source test, and you use the original V to put back the reflection via the backward program post, you will obtain the original source S. So this means if there is no change in the view side, there should no change in the source side. For the second property, if you provide the original source as updated VOV param to the backward program post to obtain the updated source S param, you can recover the updated VOV param by apply the query get over the updated source S param. In the next slide, uh, slide 4, I show you an example of bidirectional program in relational database. Get the forward program is actually a query. Suppose I have a table, a source database with relation S consists of 4 columns A, B, C, and D. I write the query get by dropping the last column D and selecting some tuple with the C value is equal to T. So I obtain the original view V. Suppose in the view side, I have some change from V to V prime with some gray deletion and gold insertion. So this change to the view should reflect back to the change in the source. For example, I have the insertion 0B0T, and this insertion should be reflect to the source with new insertion to the S prime 0B0T and D1. I copy the value of uh, the top insertion tuple in the view side, and for the missing value in the column D, this could be filled with arbitrary thing. For the deletion of 1B1T in the updated view, this reflect to another deletion to the updated source. So this is just the example, an example of doing the view update, and the pool program is generally called the view update when we deal with a relational database. In the next slide, slide 5, the thing more complicated if functional dependency introduced in the relation source of view. For example, I have a functional dependency fs that determine two dependency A to B and A to D in the original source. So this causing some constraint for data. For example, two tuple in the source with the same value of A should have the same value of B and D. The functional dependency for updated source also sharing the same functional dependency for the original one. And now in the updated view, I have a new insertion. The 1B2T, the second gold rows in the bottom right. And if I do the backward, the view update, and do the similar thing as the previous slide, so I copy some similar value of A, B, and C and fill the missing value of D with D1. So you can see two tuple in the X rows. They are conflict on the dependency A to B, or 1B1 conflict with 1B2. In the next slide, to resolve the conflict, we need some extra effects. This extra effect is the extra change causing by functional dependency. In this slide, in the updated source, I did an extra deletion, an extra insertion. And if you look at the updated source now, all of the data, the golden and the no color rows agree on a functional dependency A to B and A to D. And if you apply the query get over the updated source as param by dropping the last column and selecting on a tuple with a C value is equal to T, you can recover the updated view V prime. One of the property of where we have this. Next slide, I would like to talk about the challenge. There is a fact that it's difficult to handwrite the well behaved bidirectional program, the well behaved pair of get and put. We generally familiar with writing a query get, but this is typical to write a view update program put, and the thing more difficult if the functional dependency constraint and it has some effect when we write the view updates. We could use some example-based synthesizer to generate a get, a query get, and a view update program put. However, existing synthesizer are almost irrational. They are normally one-way synthesis, and they cannot guarantee the well-behavedness between two independent program get and put. In the next slide, I give an overview of a process and modern example by Datalog synthesizer, and later you will see process cannot synthesize bidirectional programs. Process is Datalog synthesizer, and Datalog is a set of rules. Each rule express a logic formula. You can trace from the right to the left, as the right hand side infers the left hand side. Process reduce the synthesis problem to the rule selection problem. Given the I/O example, input/output example, given a fixed set of candidate rules, process try to find a subset of the given candidate rules. In the right-hand side of the slide, you can see the output program consists of three rules. That is all the zero in the candidate rules. Next slide, slide 9, I show you the idea of a process and a challenge to use process. First, we need to have some predefined templates using the template to generate the candidate rules for process. And second, inside the process, there are two blocks, a instruction for Z3 and a logic processing block. The logic processing will maintain a synthesis constraint. They ask Z3 for the certification problem, and Z3 model the problem with some value of true and false corresponding to a rule is selected or not selected. And this selection of rule push to the software Datalog evaluation. Software evaluates the selection of the rules that evaluates the programs and return the program is consistent with example or not, and include with some feedback if it is not consistent. One of the challenge to use ProSynth is preparation of the good templates for generating the candidate rules. This challenge make difficult for ProSynth to directly synthesize the bidirectional program because we cannot use the common templates for both query and view update. And if and normally the suspect templates, the candidate rules for synthesis of get input have no clear relationship. That's why the web business property does not achieve. In the next slide 10, uh, I say about some observation and our idea. The first one, um, when we design the templates, when we define templates, we should somehow we move the web needs inside the template. So if the web needs is embedded in the template, so we have a better constraint between the subspace of synthesis of two programs. And second, there is an interesting property is a composition of well-behaved bidirectional programs is well-behaved. This means if we have many smaller bidirectional programs that are already well-behaved and compose them together, we have a bigger program that is also well-behaved. And on relation, we know the forward program that is actually a query, and as a standard, we can decompose query as a set of atomic query to be small or to be atomic. And in the database community, we know that there are existing studies on view update strategies against each atomic query. And with this strategy, we encode this strategy as the template. All of the where we have this property for bidirectional program will be embedded in the templates, and using this kind of templates is maybe good for synthesis of a web bidirectional program. Next slide 11. I give you a big picture about our approach. We focus on the synthesis of bidirectional programs from example on relation with functional dependencies. Uh, to output the bidirectional program, we require user provide one schema set with a schema of the source S, view V, and some information about functional dependency attached to the source. We don't want to automatically discover the functional dependency from the data. A second thing in the input is one example E with the table of S, V, S prime, and V prime. So from these four type of tables, we can extract the example of the query, example of V update. Our approach consists of three main steps. The first one is that in the left hand side of the big rectangle, um, we do the synthesize the query first by adapting ProSynth and using some predefined templates for relational query. So many people do about writing the query and writing the templates for query. After we have the query, we do some process on query and the given example. By first decomposing query to set up the atomic query, you can see easily decompose to the atomic get 1 to get n, and then we do a forward propagation functional dependency from the source that is already given to all of intermediate relation until we actually view. Look like we forward dependency over the query tree. And also we can forward also the example from the source to the view over the query tree, so that we have our own automatic example. The last step is to synthesize a view update program. Now we have the query, we have some information about dependency for several automatic portion. We will design some templates that encodes the minimal effect view update strategy, encodes the constraint and effect of functional dependency, and the web behavior need will be embedded in these templates. And using some templates here, we generate the candidate rules for process, and process return a, a couple of put one to put n, and we can pair with the setup atomic query get one to get n to obtain the bidirectional program. Uh, Generally, the where we have needs the important properties of bidirectional program is achieved by two things. First is where we have needs of each atomic pair that come from some template that we already have where we have need inside when we design templates. And second is the where we have needs of a composition of several smaller where we have program. In the slide 12, you can see the three blue highlight portion that corresponding to three core contribution in the paper. First is forward propagate functional dependency. Second is templatized candidates for minimal effect view strategy, and the last one is a design template encoding the constraint and effect of functional dependency. In some next slide, I will step by step give the example for three core contribution here. Next slide. First is the first contribution for what propagate functional dependency. The goal is to propagate dependency, functional dependency from the source through intermediate or middle relation to the view. Input is a schema of the source that user already provide with functional dependency, and a set of atomic query, atomic rules that is that we can obtain from adapting process and decompose the query. And output is a schema of our own intermediate relation M1, M2, and V. So all the schema in the output should be attached with a functional dependency. The idea is we for each atomic query we define how to propagate functional dependency from the right hand side of the rule to the left hand side of the rule for each atomic query rule. And if on relation in the right hand side handle, we propagate dependency to the left hand side. So in this example in the slide, so we start from the source S and propagate dependency to M1, and in the second rule we propagate from M1 to M2, and the last we propagate from M2 to V. So all of relation in the query tree, we already specify the dependency, functional dependency. In the slide 14, is about the second contribution about templatize the minimal effect VRS strategies. The goal here is to generate the candidate rules for atomic VRS. We design the template that encodes the minimal effect VRS strategy. Minimal effect is a kind of minimal change to the relation. So when we have a Z template, this template will encode some where we have needs a bidirectional program inside. Input for this step is an atomic rule. For example, I have an atomic rule here, and we need an atomic example of the corresponding query and view update. And output is a candidate rules for the atomic view update corresponding with the atomic query in the input. Next slide, I will show you how I design the templates in the slide 15. Given the atomic rule in the input, I will recognize this rule belongs to a sigma rule or selection rule that define a view V in the left hand side from a source S in the right hand side with a list of selection condition. So this is the selection rule. We check the work of Keller and Lasser. They talk about the minimal effect VRS strategy. There are a lot of strategies. One of them is if we have a new tuple that satisfies the selection condition Fi, and the new tuple is inserted in the view in the right hand side. So the I should appear in the updated source. We make some templates that encode the strategy one, and you can see in the uh, blue rules in the slide. In the right hand side of the rule, X is a vector appear in the updated view V prime. X is not in the original source, and X satisfy the selection condition because X is not in the original source and following the query in the bottom of the highlight. In the top of the highlight, you can see if X is not in the S, so X is not in the original V. But actually, in the updated view V prime, so this is a kind of insertion to the view, and it should be reflected insertion to the source. Uh, Here I use some data relation with plus and minus corresponding to keeping deletion, insertion and deletion to the relation. And later, when if you would like to compute the S prime, the updated source, we could use the original source minus some deletion and plus with some insertion. So with this template, we can generate the candidate rules by some substitution. S is in the position of M1, V is M2, and vector H, the attribute vector, should be replaced by V0, V1, and V2. This is just a simple case, but in the complex case, you can generate the attribute vector H by some function of X with the other thing. More technical thing you can find in the paper. In the next slide, 16, um, this is the first thing in the first contribution for templatize the constraint of dependency. Uh, the goal is design some templates that encode the constraint of dependency. We do not want to own a tuple in the view side could be referred to the source. Some tuple should satisfy some constraint must be possible to reflect, and the other invalid tuple should be rejected. Input is the schema with a functional dependency. For example, I have M1 with dependency from A to B. And output is a candidate rule expressing a constraint of dependencies. So this rule means if we have a two tuple in M1 with the same value of A position but different value of B position, for the other position we do not care. So a special relation FR will hold the special reject value. The idea is we use negative constraint to express the integrity constraint that is based on the VLDB20. Normally, people use the bottom choose value of false to express the negative constraint, but the proceed does not work well with null relation like bottom, some relation with empty attribute, empty variables. So we replace bottom by a special relation with that holding one attribute. It's just tricky. In the next slide, 17, besides the constraint of dependency, there are also some effect of dependencies. Um, if we have some insertion from M1, for example, 1B to T must inserted to M1 by V update, but this conflict with the tuple in the original. So there is two strategy. First is we delete the conflict tuple, and second is we revise the conflict tuple by the must inserted. So for the effect, we also need to design some templates to encode these effects to strengthen the search space. And input is a schema, atomic query, and example output is a candidate rules expressing effect of functional dependency. And depend on the example falls into what kind of uh, strategy, deletion, or revision. We generate a different class, different set of rules. So just note here, if we have a more functional dependency, so we should have automatically generate more candidate rules here. We implement a prototype named SynBP for our approach with 8,000 line of Python. Um, And we would like to answer a question that can our system synthesize bidirectional programs from example with and without functional dependency? We adapt from VLDB 2032 benchmark. Uh, i- in the slide in page 20, you can see uh, this shows the metric of the benchmark. There's at most four relation at most 30 attribute, some 16 benchmark with functional dependency, 16 without functional dependency, and some dependency is actually is a primary key. For example, the first one, and some is not a primary key. For example, in the 16, that is the benchmark 16. And the example size is considered as a reasonable size because we know Protein have some trouble with the big size example. In slide 21, we show the preliminary result. And to answer the question about the capacity of our system, we would like to say that our system can automatically synthesize 31 out of 32 benchmark. There are only one failure in the last benchmark because the query considered aggregation is not supported to uh, uh, there's not so much information about the VRS strategy for aggregation, and we cannot make some templates for that one. And for the other benchmark in this slide, you can see our system can handle a variety combination of query, just from one single query to 10 combination of 10 queries. Okay, in the last slide, uh, so in this talk, I give you an overview of our approach for synthesizing bidirectional program from example with functional dependency. There are three core contributions. Forward propagate dependency from the source to the view. Second is making some template for minimal effect via this strategy. And the last one is making some templates for encoding the constraint and effect of dependencies. The graph needs bidirectional program is guaranteed by the graph needs of templates and the graph needs of the composition. In the preliminary experiment, our system is powerful enough to automatically synthesize many interesting bidirectional programs. There are three future work. First is to study uh, the few strategy against aggregation. That is one of the failure in our experiment. Second is to templatize the more type of dependency, not only functional dependency, but also inclusion, exclusion, or domain constraint. And the last one is to seriously estimate the closeness of uh, the output program with the user intended program. So far, our program is composed of several things from, so it's a little bit complex and a big. Uh, Later, maybe we still need to optimize the output program and have some score function to estimate the closeness. Yes, so that's all for my talk. Thank you for your attention.
First, I apologize for some slides not displaying well. Are there any questions in the room or online? So I do have a question.
Yeah,
on
please.
slide 9, you mentioned provenance. Can you say,
Yes.
if, in your contributions, if you are using provenance information to... Yes, so here you, on slide 9, you said you get feedback with provenance from Soufflé. Do you use this feedback in your work?
No, I just forgot on the design templates here, which and we use this big system.
Okay, so it's used in other parts.
Yeah.
Okay. Other questions? So thank you again and for giving the talk in these conditions.